On July 16, 1945, humanity entered the atomic age with the detonation of the first nuclear device at the White Sands test site in New Mexico. With a blinding flash, the unimaginable furnace of a nuclear explosion created a new material, nuclear glass. Known as Trinitite, it is one of the most unusual substances on Earth, sitting at the intersection of physics, chemistry, and history. Hello, everyone. Giant Stonehead here. If you enjoy obscure science and forgotten history, please feel free to like, comment, and subscribe. And stay till the end for the dad joke of the week. Now, let's talk about some spicy glass. Nuclear glass refers to glassy materials formed when intense heat from a nuclear explosion melts surrounding soil, sand, and debris, which then cool and solidify into a glass-like substance. The most well-known example of nuclear glass is called Trinitite, formed during the Trinity nuclear test. Trinitite is typically described as green, glassy material composed primarily of melted desert sand, traces of material from the gadget, which was the name of the test device, and the steel tower and concrete platforms that supported the gadget. Nuclear glass is classed as anthropogenic since it results from human activities rather than natural processes. You could say, making it as a blast. The Trinity test released equivalent to roughly 21 kilotons of TNT, producing temperatures high enough to vaporize materials at ground zero. Everything not instantly vaporized was melted by the extreme heat of the fireball: copper wire, steel cable, concrete, the surrounding sand and rocks, everything. The result was a shallow crater lined with green, jade-like glass. Initially, scientists believed the glass formed simply from sand melting from the extreme heat. However, later research revealed a more complex process. Some material was melted on the ground. There was also a great deal of material that was drawn into the nuclear fireball, melted in extreme heat, after which it rained back down to the ruined ground as molten droplets, forming a thin, glassy crust. This dual process gives nuclear glass its distinct features, a structure and composition born of the chaos of nuclear fire. Let's examine the process in more detail. The formation of nuclear glass begins with the extreme heat generated by a nuclear explosion, where temperatures can exceed 1400 degrees Celsius or 2552 degrees Fahrenheit. This is enough to melt most silicate minerals that make up sand and soil. At ground zero, materials including soil, metal, and components of the bomb are vaporized or liquefied and mixed together within the expanding fireball. As the fireball rises, forming the distinctive mushroom shape, it pulls dust and sand upwards, subjecting them to intense heat that melts them completely. These molten materials are then dispersed as the cloud spreads and eventually fall back to the ground as droplets. As they descend, they cool rapidly, forming irregular fragments or thin sheets of glass. Once they reach the surface, they solidify into a vitrified layer that incorporates both natural and artificial components. Vitrified is just the process of converting something into glass or glass-like substance. The result is a heterogeneous material that reflects both the original environment and extreme conditions of a nuclear detonation. Nuclear glass is primarily composed of silicate minerals, especially quartz and feldspar, which dominate desert sands. However, what makes it unique is the presence of anthropogenic elements introduced by the bomb and its infrastructure. These materials include metals such as iron from steel structures, copper from wiring, along with other elements like aluminum, chromium, and manganese. In addition, nuclear glass can contain trace amounts of radioactive isotopes, including remnants of uranium and fission products. Scientific studies have shown that Trinitite contains both natural mineral phases and distinct anthropogenic components, making it valuable material for nuclear forensics. By analyzing its nuclear and chemical isotopic composition, researchers can reconstruct details about the explosion, including the materials used and the conditions in which the glass formed. Trinitite and similar nuclear glasses are visually distinctive. Note that atomic glasses are called atomicite when they're from sites other than the Trinity test site. Wherever they come from, they're most commonly green, although variations of color can produce black or reddish hues depending on the composition and cooling conditions. One side of a typical fragment is smooth and glassy, reflecting exposure to intense heat, while the opposite side is rougher, having been in contact with the ground as it cooled. These pieces are usually thin, often only a few millimeters to about a centimeter thick, and they frequently contain bubbles formed by trapped gases. Metallic inclusions and partially melted mineral grains can also be found within the glass, offering clues to its formation. Nuclear glass is slightly radioactive, although generally it isn't considered dangerous. Its radioactivity comes from residual fission products, activated materials altered by neutron radiation, and trace amounts of nuclear fuel, a witch's brew indeed. Over time, much of the more dangerous, short-lived radioactivity has decayed, leaving behind longer-lived isotopes that emit lower levels of radiation. As a result, most samples today exhibit only a slightly elevated radiation level compared to natural background radiation. Nevertheless, it's wise to be cautious when handling nuclear glass, especially in large quantities. Not that most of you will come across that problem unless you're, for some reason, selling it in bulk. Nuclear glass is far from a historical curiosity. It is a powerful scientific tool in several fields. In nuclear forensics, its composition allows scientists to determine the type of nuclear device used, estimate the yield of the explosion, and identify materials involved in the detonation. This makes it valuable for monitoring nuclear tests and enforcing international treaties. In materials science, nuclear glass provides insight into how substances behave under extreme conditions that are difficult to recreate in the lab. The rapid heating and cooling, combined with intense radiation, can produce unusual atomic structures, including quasicrystals. The image is a model of a quasicrystal. These rare formations challenge traditional assumptions about how atoms arrange themselves in solids. Geologically, nuclear glass offers a modern comparison for natural high-energy events such as meteorite impacts and volcanic eruptions. By studying it, scientists can better understand ancient processes that form similar glassy materials on Earth and on other planets. Although Trinitite is the most famous example, nuclear glass was formed at multiple test sites around the world. In the United States, similar vitrified materials have been found at the Nevada test site. In Kazakhstan, Soviet-era tests at Semipalatinsk produced their own forms of nuclear glass. In the Marshall Islands, tests at Eniwetok Atoll created glassy debris mixed with coral and marine sediments. One such crater is pictured here. Each of these materials reflects the local geology and specific conditions of the explosion, resulting in variations of composition, color, and structure. Nuclear glass differs significantly from naturally occurring glass. Obsidian, pictured here, is purely volcanic in origin and forms from cooled lava. Fulgurites form when lightning strikes sand, producing narrow tubular glass structures. Pectites are created by meteor impacts, where molten material is ejected and cools and travels through the atmosphere. Nuclear glass, by contrast, is formed through a combination of extreme heat, radiation, and human-made materials. It is the only type of glass that directly incorporates components of advanced technology alongside natural minerals, making it a unique marker of the modern era. Perhaps future archaeologists will find these man-made deposits and puzzle over them the way that we puzzle over the artifacts of our own ancestors. In the years following the Trinity test, large amounts of Trinitite were collected by scientists and visitors. However, due to concerns about contamination and historical significance of the site, removing Trinitite is now illegal. Much of the remaining material was buried or removed during cleanup efforts. Specimens collected before these restrictions remain in circulation and are held in museums and private collections. Their status raises broader questions about the preservation of sites associated with nuclear history and the ethical implications of collecting materials formed during such events. It is legal to purchase nuclear glass that is currently in circulation from before the ban. Nuclear glass represents a profound turning point in human history. It represents a literal fusion of natural earth materials and human technological power, formed in an instant that reshaped global politics, warfare, and scientific understanding. It also serves as a visual reminder of the immense energy released by nuclear weapons. The same forces that created Trinitite were responsible for the devastation of Hiroshima and Nagasaki. They marked the beginning of a new geopolitical era defined by nuclear capability. At the same time, nuclear glass provides scientists with a rare opportunity to study extreme physical conditions. It preserves a record of processes that are otherwise difficult to observe bridging the gap between natural geology and human innovation. Nuclear glass, particularly Trinitite, is one of the most fascinating materials ever created. Formed in the heat of the Trinity test, it captures a moment when science entered a new and powerful domain. Its existence reflects the convergence of nature and technology forged in the fires of a nuclear blast. Today, it continues to be studied for its scientific value, from nuclear forensics to material science. At the same time, it stands as a physical artifact of the dawn of the atomic age, a fragile, glassy reminder of humanity's ability to transform the Earth in an instant. But what do you think? Have you ever seen a piece of Trinitite? Have you visited the White Sands test site? Feel free to like, comment, share, and subscribe. I'll be posting here weekly. If there's anything you'd like me to cover next, let me know. Now, what you've been waiting for, the dad joke of the week. The last time I was at my girlfriend's house, I rearranged all of the labels on the jars on her spice rack. She hasn't noticed yet, but the time is cumin. Till next time, thanks so much for watching. I learned a lot making this video. I was aware of nuclear glass, but I didn't know all the details of it. I found this a little bit difficult to record due to all of the terminology and the place names being a little bit difficult to pronounce. But I had a fun time with it. I hope you enjoyed it, and I hope you'll be around next week. Till then, I really appreciate you watching, and I hope you stick around for more, because there's more coming.